So sorry for me to say that. That's on me.
Let's begin. So, what would the first one look like?
What about
Find y prime root. So it's implicit differentiation. We've been doing a lot of that over the past couple of classes, but this one involves a new rule. Last time we learned how to differentiate something that looks like 3 to the y. What is the rule, by the way? What is the rule that I'm referring to? Maybe we should start there. Yeah? Well, there.
the derivative of a to the u is equal to u prime a raised to the u and out of it.
Right. So here is when your a greater than 0 is a constant. Right? That's how we differentiate it. Okay, so now here I have a 3 to the u. Y. Okay, so go through, how do we differentiate this?
Y prime. 3 to the y. ln 3.
Alright, you follow the rule. Plus, move on, derivative of ln x.
One of that.
How do I differentiate minus x times y? Product rule, right? So I have two functions multiplying each other, x and y, and so you differentiate one, leave the other, then differentiate the other one, leave the first one, and what does that give us here?
Y plus xy.
Y plus,
Xy. Well, yeah.
no, not exactly, what are you, so the first
Oh,
one, how did you get the y?
No, okay, y plus xy prime.
Still something off, yeah.
It's supposed to be negative sign.
Should be a negative here, because technically, one way I guess you can think about it is putting this in parentheses and then doing the product rule in parentheses. But otherwise, you'd have to have a negative there as well. So probably the line would look like this, minus y minus x y prime.
Oh.
Because you'd have to distribute the negative sign on the product rule. Or you can think of the two functions as minus x and y, and so the negative sign will just carry with you. But ultimately, this is what we would get. That is us taking derivatives. Now we just want to isolate the y prime. How do we do that? It's isolate.
That's like the only
That's just
I
What if you're,
yourself.
what if you're bad at isolating?
like I know how to do the derivative, I know my rules, but like my algebra is just shoddy. So like
Yeah. Well,
So
now's the time. What are you thinking now?
you know what?
she just doesn't know.
Add
would
y to
add
the
the-
right
yeah.
side.
There you go, Greg.
I would too, Greg. Me
Take
too.
a 1
Yeah,
right there.
move that over.
Subtract, or, yeah.
This guy. Then what? So on this side we'd have left. See, so you want to isolate him, and so you leave everyone that has a y prime in it on one side. Everyone else goes on the other side. Now what?
Factor out y prime.
Y prime is the common term. You can factor that out. And then
Divide by 3y ln 3x.
Oh no, I get it.
at first I thought you felt bad isolating the y prime for some like ethical reason.
Oh,
one
no,
should be
no,
isolated
no,
a certain
no.
way.
I'm not
But
worried.
like
She's
no, you
lonely.
mean algebra wise, you're listening.
Yeah.
Okay.
I lack skills.
Yeah, well, you have a week to build them back up. It's not gonna be that bad. Just essentially try to do this. Get everyone that doesn't have the y prime on the other side, factor out the common y prime on this side, and then divide by what's left over. That's in general going to be the principle for something like this.
It's like the little thing, I try to multiply by an x,
So,
subtracting x.
I mean, so that would be a nice answer. I mean, a textbook would have multiplied by x over x and make it look a little nicer, but that's fine for me. Now, in B, now B is an interesting one. Right?
Yeah.
What are you thinking now? Do you know how to differentiate e to the x squared? How? Right, so for this guy, we have a rule. We know that to differentiate e to the u, it's just u prime e to the u. So I actually know how to differentiate that. It's just going to be 2x times e to the x squared. What about this guy, though? How do you differentiate the x to the x squared? Yeah.
Would it just be the x to the x squared times 2x times ln of x?
No. What are you doing here?
So the x to the x squared,
Yeah, but what rule are you thinking of in your head that would make that
the one
thing?
that you had there. So the dx
So
over
the-
d over dx au equals u prime.
So you're trying to apply that? So that rule does not apply in this case. And why? Yeah,
Because x is a variable and like the power is a variable too.
right. So it's very important that in this rule, you realize that your a here is a constant. It's important that it's a constant. Whereas here, it's not a constant. The base here is a variable. So that rule, this rule actually does not apply. Yeah.
Would you use the rule y prime equals x to the x, parentheses ln x plus 1? Is that a rule?
We actually derived that last time.
Yeah.
I probably wouldn't remember that as a rule, but more like I would remember the technique that I used to do that. So whenever you have the, it could give you a rule for it if you're into memorizing a bunch of stuff, but knowing the technique is actually good enough. So whenever you have the base, so if you have the base and the power is a variable, and we'll talk about some other situations. Chances are what you'd want to do is what we covered last time called log differentiation.
Oh, that's good.
Right? So pretty much to figure out this guy, so I'm going to find out what is the derivative of x to the x squared. Well, first I would set y equals x to the x squared. I would log both sides. That will allow me to bring the x squared down. And then I would differentiate both sides, y prime over y here by the chain rule. On that side, I actually need the product rule. This is going to be the derivative of x squared times the ln plus you leave the x squared, differentiate the ln. So that's 2x ln x plus x. And so my y prime is y times 2x ln x plus x. And so basically, now we know that the derivative of a sum is just the sum of the derivatives, so I now do them one by one. For the first part, I apply that rule. That's going to be 2x e to the x squared, plus for the second part, just plug this in here. So again, knowing the rules exactly very important, because if anything is off with the rules, like you have a base, a constant base versus a variable base, you have to think of these as very different things. Yes?
I don't get how the rule for e to the u is different from the rule for a to the x. Because
It's not, because if I applied that rule with e to the u, so it should be u prime e to the u ln of e.
oh, and that's just
But
one.
ln of e is
Okay.
just 1, so it just ends up canceling out.
Oh,
Right. So it's not different, it's just that the ln of e simplifies in that case. Yeah, so e is special, but it does fall in this but this does fall in this category. Now I'm going to tell you a little variation on the log differentiation in a bit. And while I could tell you a general rule for something like this, I think the formula is just too ugly. I don't think it's very practical to memorize it. But that's just me, I hate memorizing stuff. So you see something like that, where both the base and the powers are variables, log differentiation is going to be good. So maybe I should mention that in more detail. So log differentiation, I already told you how to do it. But specifically, when is it useful? Situations like I said, both base and power has variables. You can just use it in general for when you have complicated powers and you don't know how to deal with the power being a weird way. Because once you plug in the ln, it allows you to take the power down, so it's not a power anymore. It's also useful in situations where using product, quotient, chain rules are very annoying to implement. What is an example of some where one of these rules will be very annoying to implement? Well, I'm glad you asked. Part C is such a problem, right? Now, if you look at part C, yes, technically we don't need anything fancy, quote unquote, to actually get this problem done, but the outside function is a 1/3 power, so we're going to need the chain rule, but the inside we would actually need the quotient rule with the product rule, with the chain rule, all in one. That's kind of really messy. So log differentiation actually handles problems like these really nicely, right? So you wouldn't want to have to differentiate the outer function, multiply by the inside on something like that. What you can do is use a log's ability to simplify things, because it turns powers into products, it turns products into sums, it turns division into subtraction. Logarithms can simplify things very nicely. So if, as an example C, I wanted to figure out the derivative of this guy. Right, just thinking about what I would have to do to compute this is already making my head hurt, so I'm not going to even attempt that. What you could do here is set y equals that thing, which, notice that that's going to look like this. And then I can log both sides. Which is very convenient because that allows me to actually simplify this side a lot. I can take this power, move it down in front. And then I can use the rule that the log of a division is just a subtraction of the logarithms, and the log of a product is just the sum of the logarithms. So this actually breaks down into ln of x to the 7th plus ln of e to the 3x minus ln of x plus 1 to the 4th. I can break those down even further, actually, because I can take the power 7, bring it down. Ln and e cancel, so that's just 3x. And here I can take the power 4 and bring it down. Right? So just by introducing a logarithm, it allows me to actually simplify this complicated expression into just a sum of relatively simple expressions. Now I can take the differentiate. Derivative of y, ln y is y prime over y, and the derivative of these guys is, well, it's 7 times that. We know that the derivative of a constant times a function, derivative of the function times the original constant. That's 7 over x, derivative of 3x is 3, and the derivative of this is u prime over u, which is going to be 1 over x plus 1. So that's that. And then what I can do is I can multiply both sides by y. And then I can replace y with what it is here. This is going to be 1/3 times the cube root. This thing is the derivative of that function. Which looks a little bit messy, but it shouldn't have been as messy to compute. It's actually a lot easier to do it this way than to directly just brute force the chain rule here with the quotient on the product rule. It's going to be really messy. And any questions on that? Now I want to talk about an alternative to log differentiation. So it essentially will maintain all the principles that we have from log differentiation, but it's just a different way to express things, which some people might like more. So let me tell you about that. So here we can use the fact there's a way to get a log in there without actually going separate and set y equals this and do that and blah blah blah. Right. So use the fact that we had this rule from a long time ago, lecture 2, that if I have e to the ln of something, well, it's just the thing. Right? The e and the ln kind of cancel out when I move them like that. So if that actually works vice versa, right? So it means if I have something that I can actually put inside a logarithm, I could actually write it as e to the ln of that something. Right? So, for example, let's say I wanted to differentiate the same guy, x to the x, from last time. Okay? Now instead of going separately and saying set y equals this, log both sides, blah 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 blah, I could just right away, on the spot, rewrite it. Right? So I realize that the base and the powers are variables. That's going to be complicated to deal with. It would be nice to have a logarithm in there. So I just can write it as e to the ln of that thing. Like I can do that. Now what that allows you to do now is you can actually apply the rules of logarithms in the power. Right? And so that's actually going to be the derivative of e to the x ln x. And so now you can apply the derivative rule for e to the something. So this is like your u. So you know that your derivative should be u prime e to the u. Now your e to the u is actually the original function. This is just x to the x. And so now your u prime is going to be well, x ln x prime. So this ends up being, the derivative of the power is product rule, differentiate the x, leave the ln, plus leave the x, differentiate the ln, times the original function. So notice that that is the same thing we got last time. But it doesn't require you to go separately and do sep y equals this and go through all of that stuff. You can actually rewrite something on the spot. Now, the benefit of that is, again, being able to rewrite things on the spot, it saves you from, it kind of cuts down on the scratch work that you're doing. So if you go to another problem that we previously did. So what we did here was we went to the side, we set y equals x to the x squared, we did log differentiation, and then we came back and we plugged in the answer, right? So technically you didn't have to actually do that, even though you're taking advantage of the logarithm for sure, but you could actually just on the spot rewrite it. So I could just say, oh, this is just the derivative of e to the x squared plus e to the ln of x to the x squared. So I can just rewrite it with an exponential and a logarithm kind of built into everything. So I didn't need to go to the side and do something separate, I just on the spot rewrite it. And now I just apply the e to the u rule, so it's u prime e to the u. 2x times the original function. This one is going to be, well, product rule, 2x ln x plus x squared times 1 over x times the original function. So this is 2x e to the x squared plus, this is 2x ln x plus x times, the e to this is just another way to rewrite that. So it's exactly the same principle as log differentiation, just that some people might prefer to express it this way. Because you don't have to go to the side and do something and come back. You can just, on the spot, just rewrite that thing as e to the ln of the thing. Then apply your derivatives. Right? You essentially can take advantage of the logarithm without need to set up a whole side problem. So it's just another option here. So, in terms of log differentiation, you can do it the way we did it earlier in last class, or you can do it this way. Completely up to personal preference. Just pick whichever way you like better. Do it that way all the time. So, there's that. For the remainder of the class, we're just gonna actually have a little more fun. The next main topic is linear approximation, but can't really get that done in 20 minutes, so let's do something else. Let's apply what we know about, we're gonna apply this stuff along with some other things to talk about limits again. So let's talk about things called indeterminate forms. And L'Hôpital's rule. Has anyone ever heard of that before? L'Hôpital's rule? Sounds familiar? Okay, I don't remember what that is. So, indeterminate form, what is this? So, this is a limit form. So it's when you're taking a limit, so it's not just something that's going to exist on its own. Limit form that is ambiguous because of competing ideas. So what are such forms? These are forms like infinity raised to 0. Right? Why? So if I'm taking the limit of something and the answer seems to be approaching, like the base is going off to infinity, but the power is going off to 0, what's that going to be? Because a base of infinity would make you think that the answer is infinity, but you have another rule that tells you that you raise something to the 0, you get 1. Well, is it infinity or is it 1? You know, it's kind of hard to tell. So it's very ambiguous because you have these two ideas. Well, it could go this way, it could go that way. So that is an indeterminate form. 1 to the infinity, also an indeterminate form. Because again, you raise something to the power infinity makes you feel like it should go off to infinity, but base is 1 means that it should be 1, right? Another one is like infinity minus infinity. Now, some people might think of that as 0, but that's actually not the case. It turns out that some infinities are bigger than other ones. It's actually totally ambiguous. We don't know what that is. Another one. 0 times infinity is another ambiguous one. Because you're like, if I multiply by infinity, I should get infinity. But if I multiply by 0, I should get 0. What is 0 times infinity? Right? Kind of ambiguous. Another example. Infinity divided by infinity. So again, that does not always cancel and give you 1. In fact, it rarely will, because different infinities can be different sizes. That could give you infinity, or 0, or 1, or any other number in between, actually. There is another one, 0 over 0. Now, we already know that we can't divide by 0, but again, this is a limit form. So I'm just saying, you're taking the limit of something where both the top and bottom is getting closer and closer to 0. What would that actually mean? Okay? So these are the indeterminate forms, right? There are about 6 of them. And I'm very proud of myself that I remember them all. Because it's one of those things where if I see it, I'll recognize it, but if I'm off the top of my head trying to list all of them, I always forget one. There's always 5, and there are 6 of them, but I can't remember the 6th one. Yeah, I got through all of them too. This is good. Okay. So these are the indeterminate forms. Now it turns out that there's something called L'Hôpital's rule. It's a French guy. It's not even the guy who came up with the rule. I think the rule came up by one of the Bernoullis, and he was like a patron of them, so they put his name on it. But L'Hôpital's rule helps with these 2 cases specifically. L'Hôpital, and I believe this is like literally French for hospital. So I used to have some of my students go, so how do we find this limit? Take it to the hospital. Like they used to say that, I don't know. So L'Hôpital's rule helps with these 2. So it's very important that you realize that you can see any one of these 6 things showing up in a limit, but L'Hôpital's rule only helps you with these 2. So the idea is going to be, if you have one of these other ones, can you rewrite it so that it would look like one of these 2, and then apply L'Hôpital's rule? So how does L'Hôpital's rule help us deal with this equation? So let me tell you what the rule is. So it's like we're using now derivatives to help us find limits. L'Hôpital's rule says the following. And I'm leaving out some details here, but whatever. We can actually go to this. So suppose I want to find the limit as we're approaching something of f of x over g of x. Okay? So you have a limit of something being divided. And this approaches infinity over infinity, quote unquote, or 0 over 0 specifically. So both your f and g actually go off to infinity, could be plus or minus in this situation. Or both your f and g get smaller and go to 0. So if you have a limit that you're looking at and it approaches one of these two things, then it turns out that this limit that you're looking at, limit as x approaches a f of x g over g of x, is actually going to be equal to the limit of f prime divided by g prime. Okay, so again, there's a bunch of stuff I should have set up here. Ooh, suppose f and g are differentiable, blah, blah, blah. There's continuity requirements, but you usually won't have to worry about those in these class. But the idea is, if your limit approaches one of these two values, then it turns out that that original limit is going to be equal to the limit that you would get by just taking the derivatives of each part separately. Right? So you're not applying the quotient rule, but it actually turns out that the derivatives are going to behave like the original functions in the limit. And that's called L'Hopital's rule. So let's see some examples of this being applied. So suppose I wanted to find the limit as x approaches infinity of e to the x of x. So it turns out all of these limits give rise to indeterminate forms, and we are going to use L'Hopital's rule. To actually compute them. So it's a nice little application of derivatives to limits, and oftentimes it's also going to be very convenient to use the trick. A lot of times to rewrite these guys as one of those guys, they're going to kind of use the trick that I mentioned before with log differentiation or writing some expression as e to the ln of that expression. You can use those tricks to change from these forms to that form. So go through the first two very quickly, because these are actually two, A and B are ones that you should actually be able to see the answer in your head. I don't remember how much you guys remember about limits, but you need to remember by Friday. So, anyone want to take a guess at what the first one is going to be?
Infinity over infinity.
Right, it approaches infinity over infinity, but what's the answer? Do you know what the answer is? By looking at it? Yeah?
Is it infinity?
Why? What's your reason?
Because the derivative of e to the x is e to the x, and then the derivative of x is 1, and then
Okay. So you're applying L'Hopital's rule. So as x goes to infinity, e to the x goes off to infinity, and x itself goes off to infinity. So this goes to infinity over infinity. So what you can do is, I know L'Hopital's rule helps me with that situation. This guy is going to be equal to the limit of the derivative of the top, which is e to the x, over the derivative of the bottom, which is 1. And on the equal sign, I usually write like L apostrophe H to indicate to the reader that, hey, I just applied L'Hopital's rule here. And of course, now if you let x goes off to infinity, infinity is going to be the answer. So it turns out infinity over infinity didn't cancel each other, it actually goes off to infinity. Because it turns out the top infinity is a lot bigger than the bottom infinity. which isn't necessarily clear in the beginning. However, the shortcut that I was thinking of is, remember I told you guys how polynomials and exponentials relate to each other? Like polynomial is super small compared to an exponential. So when you're going off to the infinity, the e to the x is way up here and the x is way down here. So that's like the numerator is huge compared to the denominator. So you expect it to kind of go off to infinity. Exponentials are going to grow faster than polynomials. Similarly in B, if I looked at the limit as x approaches infinity of ln x over x, now you could eyeball this and know that that would be 0, because we also learned that logarithms grow a lot slower than polynomials. So as we're going off to infinity, x is going to be up here and ln x is going to be way down here. So the top is very small compared to the bottom, and the bottom is going off to infinity. Density is going to go off to 0. But let's say you didn't eyeball that and catch that. You would, of course, hopefully know that ln approaches infinity as x approaches infinity, and x obviously approaches infinity as x approaches infinity. So this is an indeterminate form, right? The limit approaches infinity over infinity. L'Hopital's rule tells us how to deal with that, though. We can just differentiate the top and the bottom. Derivative of ln x is 1 over x. Derivative of x is 1. Which now, that's just the limit as x approaches infinity of 1 over x, which hopefully we know is 0. So that limit is 0. So these two, it's nice to kind of showcase the method, but they're not that interesting because you could actually just eyeball it and know the answer right away. Problem C starts out being interesting though. What does this approach? As x is approaching 0, what does this look like? What is the form of the answer going to look like?
Zero over zero.
There's no division.
Yeah.
So x is approaching 0. Well, what is this? Yeah, but what's the form? Can you see the form? Well, there are two parts, right?
Yeah.
What is each part doing? What is the first part getting close to?
0.
0. What is the second part getting close to?
Infinity.
Well, negative infinity, technically. Right? So this is a 0 times infinity form. It's indeterminate. Right? So it's a 0 times infinity. Okay? Now, ahead of time, I don't know what that is. But at the same time, L'Hopital's rule doesn't help me with this situation. Why? Because L'Hopital's rule only helps with 0 over 0 or infinity over infinity. This is 0 times infinity. So what can I do to figure this out? Well, here's something we can do. I'm going to take the x and move it to the denominator, and I can do that by doing this. Write the x as 1 over x and move it to the denominator. Now, of course, your x isn't 0, we're approaching 0, so I'm not worried about actually doing that. But yeah, by keep, change, flip, this is exactly equal to the original, right? As long as our x is not 0. And in this case, it has to be strictly greater than 0. Let's move from 0 to the right. Okay. Now, what's nice about that is, what's the form now? What's the top approaching? Negative infinity. What is the bottom approaching? One over x as x approaches 0 from the right. What is that approach?
Approaching an infinity. It's to fit L'Hopital's rule.
Well, you can't just like say, well, it should fit. No, you have to.
Is it 0? 0
Well, what does 1 over x look like? Do you remember?
Nope.
It's like a long time, you know? What does 1 over x look like? There's a picture for 1 over x look like. Almost, you're half right. The other half.
Huh? How does that, how did you say?
She went like this. 1 over x squared looks like that, not 1 over x.
It's like,
But there- yeah.
It's
yeah,
like
yeah, yeah, yeah.
understand.
You read my mind, it's like on the same page.
It's crazy.
Right? So that's what the graph looks like. Now if I'm approaching 0 from the right side, what's happening to the graph? It's going to infinity, it's going up to positive infinity. So you need to remember that. So this is an infinity over infinity form. So by me just doing my little algebra magic here, I went from a form, it's still indeterminate, but it's better than that one because I have a rule that helps me with this one and I don't have a rule that helps me with that one. So I did this little sleight of hand here to get it into a form where now L'Hopital's rule actually applies. I can now apply L'Hopital, take it to the hospital, and you just now differentiate the top, differentiate the bottom. So now the derivative of the top is 1 over x, we know that. The derivative of the bottom is minus 1 over x squared. Now what you'll notice is that I can do keep, change, flip on that guy to simplify it, and it just simplifies to minus x. And of course, as x is approaching 0 of minus x, well, that is 0. This answer is actually 0. So in the 0 times infinity, in this particular battle, the 0 wins out. And again, you know, polynomials move faster than logarithms, so basically this guy's going to 0 a lot faster than that guy's going to infinity. And so the 0 wins. So you can try the others. So this isn't on your test on Friday, strictly speaking, but I'll like throw in some problems in the bonus section on L'Hopital. So try the rest of these, we'll pick up on that tomorrow. That's the full application.